Okay, it is the book problems for the chapter on solutions. Let's get started right away. First question. The solubility of a gas in water is 6.16 grams per liter at 104 kilopascals. What is the solubility when the pressure of the gas is increased to 288 kilopascals? Here's the equation. S is solubility, P is pressure, and it's in kilopascals. There's the plug-in. And then solve for S2. Very simple. And cross multiply and divide, and the answer is 0.44 grams per liter. Notice that the solubility is in grams per liter. A gas has a solubility in water of 0.0 degrees Celsius and 3.6 grams per liter at a pressure of 1 atmosphere. What pressure is added to produce an aqueous solution containing 9.5 grams per liter at the same gas at 0 degrees Celsius? There's the plug-in. Solve for P, 0.44. Okay, now, number 3. It says, what determines whether a substance will dissolve? Well, polarity of the solvent and the solute, chemical composition of the solute and solvent, that's correct. What determines how fast the substance will dissolve? Temperature, surface area, agitation, particle size, all very good. Okay. And then it says, what units are usually used to express solubility of a solute? A variety of units are used. Right now, we're using grams per 100 grams of solvent. What are 2 conditions that determine the mass of solute that will dissolve in a given mass of solvent? Temperature and pressure, if the solute is a gas. Temperature and pressure, if the solute is a gas. What would you do to change? A saturated solid liquid solution to an unsaturated one. Pour some more solvent in. Add solvent. Very good. B. Looks like B's coming up. A saturated gas liquid solution to an unsaturated solution, relieve some of the gas. Unsaturated. Okay, so it would be increase the pressure. Increase the pressure. The solubility of a gas is 0.58 grams per liter at a pressure of 104 kilopascals. What is the solubility if the pressure is increased to 250 kilopascals at the same temperature? And this is just simply the same thing we did, S1 over P1, S2 over P2, etc. And then cross multiply and divide. A solution has a volume of 2 liters and contains 36 grams of glucose. If the molar mass of the glucose is 180, what is the molarity? Molarity is moles over volume. In this case, it's going to be the moles is mass over atomic weight, and the liters is milliliters over 1,000, and it's going to be plug in, and then 36 divided by 180, and then divided by the volume is going to be the right answer. A solution has a volume of 250 milliliters and contains 0.7 moles of sodium chloride. What is the molarity? There's the equation, there's the plug-in, and then the answer, 2.8 molar. So 0.7 divided by 0.250. How many moles of ammonium nitrate are in 335 milliliters of 0.425 ammonium nitrate? There's the equation, and there's the plug-in coming up, and you're looking for the moles, how many moles, and then the answer is listed there. Okay. Next, how many moles of solute are in 250 milliliters of 2 molar calcium chloride? How many grams of calcium chloride is this? There's the equation. There's the calculation. 2 times 0.250 is going to be 0.5 moles. And then you simply find out what is the mass of 1 mole. So it would be 0.5 moles of calcium chloride, which is 110, which would be 55 grams. Would be 0.5 moles of calcium chloride. 12. How many milliliters of solution of a 4Ki are needed to prepare 250 milliliters of a 0.76 molar Ki solution? There's the equation. It's going to be the molarity times the volume equals the molarity times the volume, case 1 and 2. And then you're going to plug into the equation. I'm calling 4 molar M1 and V1 we're looking for. Plug into the equation and rearrange, multiply, in other words, cross multiply and divide, and V1 equals 0.048 liters. Okie doke. Or 48 milliliters. Next. How could you prepare 250 milliliter of a 0.2 molar sodium chloride using only a solution of 1 molar sodium chloride solution? There's the equation. Again, you're going to plug in 250 milliliters. You could change it to liters or keep it in milliliters. It doesn't matter, depending on what they're given. So I simply changed it, but it doesn't matter, as I proved in class. So now you're going to solve for V1, and that's going to be 50 milliliters. Right. Use a pipette to transfer the 50 milliliters of 1 molar solution to the 250 milliliter volumetric flask, then add distilled water up to the correct mark. If 10 milliliters of propanone is diluted with water to a solution volume of 200 milliliters, what is the percent by volume of propanone in the solution? So it's volume of solute divided by volume of solution, not volume of solvent, volume of solution times 100, and that's going to equal 5%. Make sure both volumes are in the same unit labels, both liters or both mLs. A bottle of antiseptic hydrogen peroxide is labeled 3%. How many milliliters of hydrogen peroxide are in 400 milliliter bottle of this solution? Okay. Well, it's going to be percent by volume equals volume of solute divided by volume of solution times 100%, and it's going to be 0.3 is going to equal, you got to take that out of percentage, and the answer is 12 milliliters. Don't forget to take it out of percentage when you enter the correct multiplication. How do you calculate the molarity of a solution? If the number of moles of the volume, if the number of moles and the volume of the solution is known, its molarity is determined by dividing the moles by of the solute by the volume of solution. Compare the number of moles of solute before dilution with the number of moles of solute after dilution. What we're going to do is we're going to look at the relative density of the distribution of solute before and after the addition of solvent. Diluting a solution reduces the number of moles of solute per unit volume, but the total number of moles of solute in solution does not change. What are two types of expressing the concentration of a solution as a percent? Well, we're going to look at volume of solute over volume of solution and mass over mass of solution. Express the concentration as a ratio of the volume of solute to the volume of solution, volume over volume, or as the ratio of a mass of solute to the mass of solution. Calculate the molarity of a solution containing 400 grams of copper-2 sulfate in 4 liters of solution. Well, the first thing you're going to have to do is you're going to have to recognize what the formula is. and there it is. And we're going to use the one on the far right, and that is going to be the mass of copper 2 sulfate divided by the atomic weight of copper 2 sulfate. So you add up the mass, the atomic weight of copper 2 sulfate, which is 136 grams, so it's going to be 400 over 136, and they, instead of giving you milliliters, they give you liters directly, which helps it out tremendously. So you do 400 divided by 136, and then divide everything by 4, and it's 0.627 molar copper 2 sulfate. Now, traditionally, molar solutions are generally given to 3 significant figures, generally. Oftentimes, it's 3 significant figures. Any more than that is a waste. How many moles of solute are present in 50 milliliters of 0.20 molar potassium nitrate? Now, when the molarity is exact, it's oftentimes 2 significant figures, like 0.20 instead of 0.200. Well, there is the equation for the calculation. And so we're going to find the number of moles, so it's going to be 0.2 times 0.05, which is the liters. That's going to be 50 divided by 1,000 is 0.05, and 0.2 times 0.050 is going to be 0.01 molar, 0.01 molar KNO₂. How many milliliters of a stock solution of 2 molar potassium nitrate would you need to prepare 100 milliliters of a 0.150 molar potassium nitrate? So this is going to be a dilution problem, and there is the equation M1 times V1 equals M2 times V2, kind of like a gas problem where you have first conditions and second conditions. Of course, it's not a gas problem, but the same idea in terms of the equations. Now, you just have to simply pick what conditions you want which, and make sure that your molar volumes and the volumes that you're taking are the same condition. So there you're plugging in on the right, upper right, and then cross multiply and then divide, and sorry, not cross multiply and divide. So you're just simply dividing through by 2 molar. You're dividing the left side through by 2 molar, and you're getting 0.0075 liters or 7.5 milliliters. Okay, now, number 22, 7.5 milliliters, that's the answer. Okay, a little redundant. Just make sure that the conditions are the same. Okay, so 2 molar, you're asking how much of that, so that should be, the unknown volume should be with that 2 molar. What is the concentration in percent by volume of a solution containing 50 milliliters of diethyl ether in 2.5 liters of solution? So it's going to be the volume of solute, which is 50 milliliters, so that's going to be 0.05 liters of diethyl ether divided by 2.5 liters of solution. So the percent by volume, that's how you read that. What is the percent by volume of the solute in the solution? So it's going to be a 2% solution of diethyl ether, meaning that 2% of the solution is diethyl ether by volume. That's how you read that. A 2% solution of diethyl ether by volume. How many grams of potassium sulfate would you need to prepare 1,500 grams of a 5% potassium sulfate by mass solution? So what you would do is, you know that you're going to put the mass of the solute over the mass of the solution. So you're going to have, what is going to be the mass of solution? So here we have the mass of solution. Notice that I'm taking it out of percentages. So it's best to work with the decimal equivalent of the percentage when you're given the percentage and you're trying to find something else. So here you have 1,500 grams of solution, and 0.05 is the fraction of the solute to solution. So it's 1,500 times 0.05 is going to be 75 grams of potassium sulfate. Notice that you're taking it out of percentage when you're utilizing. It's just easier to do it that way. There's a mathematical equivalent using the 100, but it's kind of a waste of time if you have any kind of skill in math. What are three colligative properties of solution? So that's what this chapter is really heading to, is colligative properties. Section 3 is colligative properties. So it's all a build-up to colligative properties. Vapor point, vapor pressure lowering, which will affect the boiling point elevation and the freezing point depression. What factors determine how much the vapor pressure, freezing point, and boiling point of a solution differ from those properties of the pure solvent? What properties, what factors determine? The number of solute particles dissolved in the solvent. Notice it says solute particles, a hint for later. Sucrose doesn't dissolve, doesn't dissociate, so it's only one particle, where salts, ionics compounds will. Sodium will be 2 particles, calcium chloride will be 3 particles. Would a dilute or a concentrated sodium fluoride solution have a higher boiling point? Explain. The more particles you put into solution, the greater the change in the colligative property. Concentrated sodium fluoride, because the magnitude of the boiling point elevation is proportional to the number of solute particles dissolved in the solvent. And sodium fluoride, for every mole of sodium fluoride, you get 2 moles of particles. An equal number of moles of potassium iodide and magnesium iodide are dissolved in equal volumes of water. Which solution has the higher boiling point? It would be magnesium iodide, because you have more particles. For each mole of magnesium iodide, you have 3 moles of particles. So for every mole of potassium iodide, you only have 2 moles of particles because of the dissociation. So the next would probably be another colligative property, such as freezing point, or vapor pressure in this case. And let's wait and see. What prevents something from going into vapor? Water, for instance. These are ionic compounds, so we're going to water. So potassium iodide solution, but why? Why? An equal volume of moles are dissolved in which would have a higher vapor pressure. Well, the potassium iodide would affect it the least, so it would be higher. If you put magnesium iodide in there, magnesium iodide is going to have 3 moles, 50% more particles, so it will have a greater effect. And the freezing point depression, which will have a greater freezing point? Again, the potassium iodide. They're kind of working backwards. It's freezing point depression, and the greater the number of particles, the greater the depression. So magnesium iodide would have a greater depression, therefore the higher freezing point would be potassium iodide. Explain why the vapor pressure, boiling point, and freezing point of an aqueous solution of a non-volatile solute are not the same as those of the pure solvent. Formation of solvation shells around solute particles reduces the number of water molecules with sufficient kinetic energy to escape the solution. Therefore, the vapor pressure is lower relative to the pure solvent. More energy must be supplied to reach the boiling point. Therefore, the boiling point is elevated relative to pure solvent. Solvation shells interfere with the formation of hydrogen-bonded ice structure. This results in a depression of the freezing point relative to the pure solvent. How many grams of sodium fluoride are needed to prepare a 0.4 molal sodium fluoride solution that contains 750 grams of water. The equation for molality, small m, as opposed to molarity, large M, is moles over kilogram of solution. And what you have is, you have the mass over the atomic weight is going to be divided by the grams of solvent divided by 1,000. So here we don't know the mass of sodium fluoride, and we have 0.4 molal solution, and we have cross multiply, and we have 0.4 times 0.75 times 42 ultimately would be the mass of the sodium fluoride solution. So you're simply cross multiplying twice, essentially. So the 0.4 times 0.75 times 42 would be 12.6 grams of sodium fluoride. Calculate the molality of a solution prepared by dissolving 10 grams of sodium chloride in 600 grams of water. So the equation that you're going to set up is going to be the expanded version, which has the mass over atomic weight and then the grams over 1,000. And you're going to plug in 600 for the grams, and then 10 grams for the mass of sodium chloride, and then 58 for the mass of the atomic weight of sodium chloride, and then it would be 600 over 1,000, or 0.6 kilograms, and that's going to equal 0.28 molal. Now, notice, though, just to get you ready for the colligative property of freezing point depression and boiling point elevation, and that is that solution is 0.2 molal relative to looking at sodium chloride as a single particle, but it ionizes into two particles. Just keep that in mind. What is the mole fraction, which we haven't done yet, of a compound in a solution made of mixing 300 grams of ethanol, which is the solute, and 500 grams of water? So the mole fraction is going to be XA sub A, which is what we're looking for of each component. The first one we're going to do is ethanol, and it's going to be the moles of the ethanol, because that's what we're looking for, divided by the moles of the ethanol plus the moles of water. And then we'll do the same thing but for water. Now there's the moles. Now you know that a mole is mass over atomic weight, so that's how you get that value. That's right out of the book. The equation you get is XA equals NA over NA plus NB, and then the mole fraction of ethanol is going to be 0.19. Now, how do you find the mole fraction of water? Well, now, let's say we're saying of water now. So XA is water, correct? XA is water. Now, so then it would be the moles of water divided by the moles of water and ethanol. So it's going to be the moles of whatever it is you're looking for divided by the sum of the moles of each component. Now, again, this is the equation, XA, and that's going to equal NA over NA plus NB, and XA is going to be the mole fraction of the water this time. Okay, so you see there quite clearly that it's X of water sub H₂O yields the moles of water over the sum of each component, the moles of sum of the moles of each component, and that's going to be 28 divided by 28 plus 6.52, which is 0.81. Now, notice that the sum of the mole fractions is going to equal 1. So we could have done this the easy way and said 1 minus the mole fraction of ethanol equals the mole fraction of water. And the next time we do this problem, we'll do that. A solution contains 50 grams of carbon tetrachloride and 50 grams of chloroform. Calculate the mole fraction of each component in the solution. Now, I don't particularly remember if I think I did. Yes, I did this the easy way. So I'll let this run for about a minute and see if you can come up with the answers before this is over. Don't forget to convert 50 grams of each component to moles. So then it's going to be XB, which is going to be the chloroform, is going to be 1 minus the XA. Okay, just keep you in the loop there. So the mole fraction of carbon tetrachloride is going to be 0.33 moles divided by 0.33 plus 0.47, and that's going to be approximately probably, I'm guessing, 0.4, 0.37. I may be way off. Let's see. 0.41, not bad. So then the mole fraction of the chloroform will be 1 minus 0.41, which will be 0.59. So the answer to the next, the mole fraction of the chloroform will be 1 minus 0.41. Remember, the sum of the mole fractions of each component, solute and solvent, in the solution must equal 1. So 1 minus 0.41 is 0.59. What is the freezing point depression of an aqueous solution of 10 grams of glucose, that's C₂H₂OH, in 50 grams of H₂O? Now don't forget, glucose does not dissociate. So the equation is delta TF, that's the freezing point depression, equals KF times M, the molality. So it expands to KF times M over atomic weight divided by G, the number of grams over 1,000. The constant for the freezing point depression for water, it's water specific, is 1.86 degrees Celsius over M. We're plugging in, and remember, 1 mole of a non-dissociating substance will give you 1 mole of a non-dissociating substance. So 10 over 180 divided by 0.05, and that's going to be 2.1 degrees Celsius. So that's the freezing point depression. So the temperature would be negative 2.1 degrees Celsius. Calculate the freezing point depression of a benzene solution containing 400 grams of benzene and 200 grams of molecular compound acetone. The Kf for benzene is 5.12 degrees Celsius per molal. So this is the equation for the calculation of the freezing point depression. Here I have just plugged in 200 over 58, 58 being the atomic weight of acetone, and the 400 milliliters of solution. Calculating it out, you get 44 degrees Celsius. Make sure you can set this equation up, very similar to water, but with a different Kf. And remember, it's not an ionic substance being dissolved, so it doesn't dissociate. What is the boiling point of a solution that contains 1.25 moles of calcium chloride in 1,400 grams of water? Well, I am modifying the equation for the boiling point elevation by multiplying Kfm by the number of ions that are going to actually dissociate. And the only difference between this and another one is that now it's going to be 1.4 kilograms instead of 1 kilogram because it's 1,400 grams. So it'll be 3 ions times 0.512 times 1.25 over 1.4, and that's going to be 1.37, and then the boiling point will be 101.37 degrees Celsius. So just remember, you got to put in the number of ions that are forming. What mass of sodium chloride would be dissolved in 1 kilogram of water to raise the boiling point 2 degrees Celsius? So now I want to determine the mass of sodium chloride, knowing that the atomic weight is 58. So cross multiply, so it's 3.9 equals the mass over 58, and then cross multiply again, 3.9 times 58, which is going to be approximately 4 times 60, which is 200. 3.9, 4 times 60 would be 240, so it would be a little less, 226.6 grams. So that would be the mass. Okay. No need to worry about the number of ions dissolved. So the sodium chloride dissociates into 2 ions, so only 1/2 of that amount is going to be required. So where you don't have to put it into the original equation, you have to be mindful of the fact that you don't need all 226.6 grams. You only need half of that, and that's the answer. What are 2 ways of expressing the ratio of solute particles to solvent particles? So you can, actually there's more than 2 ways. You have molality and mole fractions are 2 convenient ways of expressing the ratio of solute particles to solvent particles. So those are the basic ways. You can also do other ways of concentration. How are freezing point depression and boiling point elevation related to molality? Well, it's going to be, freezing point depression is direct relationship. The magnitude of freezing point depression and boiling point elevation of the solution are directly proportional to the molal solution when the solute is molecular, not ionic. How many grams of sodium bromide must dissolve in 400 grams of water to produce a 0.5 molal solution? All right, so now we're going back to simply a molal solution. So it's going to be 0.5 molal equals 400, would be X grams over the atomic weight over 0.4 kilograms. And that's exactly what it is. So it'd be 0.5, cross multiply, 0.5 times 0.4, and then cross multiply again. The product of 0.5 times 0.4 and then times 103, and 0.5 times 0.4 is 0.2, and then times 103, which is approximately 20 and change, so 20.6 sounds about right. So it'd be 20.6 grams. However, do you need all of that? Remember, we have sodium bromide, but that's only relative to freezing point depression or boiling point elevation. That's when we worry about the number of ions. Calculate the mole fraction of each component in a solution of 2.5 molar ethanoic acid, which is CaCl₂OH in 10 moles of water. So it'll be 2.5 times the product times the sum of 2.5 plus 10, and then what you can do is then you can say that that's XA, and then XB would be 1 minus XA, because remember the 2 fractions has to equal 1. So 2.5 divided by 12.5 would be 0.2, so that XB would be 0.8. XB would be 0.8, or in other words, the fraction of ethanoic acid is going to be 0.2, and the fraction of water is going to be 0.8. A is ethanoic acid and B is water. Number 41, moving right along. 41, we have, what is the freezing point of a solution that is 12 grams of carbon tetrachloride dissolved in 750 grams of benzene? The freezing point of benzene is 5.48 degrees Celsius, and the Kf is 5.12. There's the equation. Remember, N is going to equal 1 because it doesn't dissociate. Okay, it doesn't dissociate. The carbon tetrachloride does not dissociate, and so it's going to be 5.12 times 12 divided by 152 over 0.75. So the freezing point depression is going to be 0.54. So the freezing point will be 5.48 minus 0.54, which is about 4 and change. So it'll be 4 point whatever. Let you do it. You have a calculator. So it'll be 4.94 degrees Celsius. So 5.48 minus 0.54 equals 4.94 degrees Celsius. Next, name and distinguish between the two components of a solution. Name and distinguish between the two components of a solution. Well, I don't know where they're going with this, but obviously it's going to be, I hope you know by now, the solvent is the substance in which the solute is dissolved, or the solute is dispersed and the solvent does the dispersing. Explain why the dissolved component does not settle out of solution. Because the solute is less than 1 nanometers and it is solvated by the water, and the water actually holds it. Random collisions of the solvent molecule with the solute particles provide enough force to overcome gravity. Plus, you have the solvation process, where it's literally surrounded and kept afloat by the water. Define the following terms: solubility, saturated solution, unsaturated solution, miscibility, and immiscibility. So you're going to have to kind of relate the terms by when you define them. Solubility is the amount of substance that dissolves in a given quantity of solvent at specific conditions of temperature and pressure to produce a saturated solution. So that's solubility. Saturated solution, a solution containing the maximum amount of solute for a given amount of solvent at a constant temperature and pressure. Right. Next, unsaturated solution is a solution that contains less solute than a saturated solution at a given temperature and pressure. Miscible describes liquids that dissolve in each other, and immiscible describes liquids that are insoluble in each other. Number 45, coming up next. If a saturated solution of sodium nitrate is cooled, what change might you observe? Well, it would become possibly a supersaturated solution, and then if you drop the particle in there, maybe the solute will crystallize out, or maybe the excess material will just precipitate out as the temperature decreases. Can a solution with undissolved solute be supersaturated? Can a solution with undissolved solute be supersaturated? Generally not. If it's If it's got some undissolved material, that means it's saturated. No, if there is undissolved solute, the excess solute would come out of supersaturated solution. 47. What mass of silver 1 nitrate can be dissolved in 250 grams of water at 20 degrees Celsius? Now, you want to use table 16.1. There's 16.1. You want to find silver nitrate, which is silver nitrate, silver 1 nitrate, or it'll probably be just silver nitrate. There it is near the bottom, 5 up, 6 up from the bottom, and you'll see that at 20 degrees, so you go over to the 1, 2, 3, 4th column from the left, 3rd column from the right, and you'll see that it's going to be 222 grams per 100 cubic centimeters of water, or 555 per 250 cubic centimeters, okay? What is the effect of pressure on the solubility of a gas in liquids? Well, if you are at the store and solubility increases with pressure. If you have water under pressure, you feel the pressure of the seltzer bottle. You shake it and you feel that pressure, and bubbles stop coming out of solution. I'll get back to that in a minute. The solubility of methane, the major component of natural gas in water 20 degrees Celsius in 1 atmosphere, is 0.026 grams per liter. If the temperature remains constant, what will the solubility of this gas at the following pressures be? 0.6 atmospheres. There is the Henry's law equation, S1 over P1 equals S2 over P2. Plug in for the values, and we get 0.026 divided by 1 equals S2 over 0.6. Cross multiply 0.026 times 0.6 divided by 1 is 0.0156 grams per liter. Notice that grams per liter is used exclusively for the solubility of a gas. And the solubility of a gas is recognized as just S. The next one is B, and there's Henry's law equation. So you're going to see an increase in solubility. So you have 0.026 grams per liter at 1 atmosphere. So you're going to see that increase because the solubility in grams per liter of a gas is directly related to the pressure. Higher pressure, higher solubility, etc. So you go from 0.026 grams per liter to 0.0468 grams per liter. So there you have it. Knowing the molarity of a solution is more meaningful than knowing whether a solution is dilute or concentrated. Knowing the molarity of a solution is more meaningful. Dilute and concentrated are relative terms and are not quantitative. Molarity provides the exact number of moles of solute per liter of solution. Define molarity, then calculate the molarity of each solution. Define molarity, then calculate the molarity of each solution. Okie dokie. So, molarity is the number of moles of solute dissolved in 1 liter of solution. Now I want to calculate the molarity of each solution. Well, I don't know. Oh, here it is. Okay, 1 mole divided by 0.75 liters is going to be, then you calculate that out, and you say 1 divided by, you don't need the expanded equation, you can just use the first one, moles per liter, where the number of liters is 0.75, So it's 1 divided by 0.75, and that's going to be 1 divided by 0.75, and you should be able to do that one quite readily in your head. So it'd be 4/3, so it'd be 1 1/3, and that's exactly what it is, 1.33 molar. B looks like 0.5 moles of magnesium chloride in 1.5 liters of solution. So it's going to be 0.5 divided by 1.5 is going to be the answer. So 1 divided by 3/2. 1/2 divided by 3/2. So it'll be, what is half of 1.5? So 1.5 divided by 1.5. So get out your calculators and see if you can estimate it first. Gave some hints, and the answer is 0.33, a third. It's a third, because 0.5 is 1/3 of 1.5. So you should be able to do that one using some clever mental math. Okay, how many milliliters of 0.5 molar potassium chloride solution would you need to dilute to make 100 milliliters of 0.100 molar potassium chloride? So the dilution equation is going to be M1 times V1 equals M2 V2, and so you're going to have 0.5 V1 equals 0.1 molar times 0.1 liter. So you're going to get 0.1 times 0.1 divided by 0.5, and that's going to be V1. So pretty straightforward. Divide through by 0.5, the product of 0.1 times 0.1, and you get 20 milliliters. Calculate the moles and grams of solute in each solution. 1 liter of 0.5 molar sodium chloride. Well, so it will be 0.5 moles, and you could cross multiply and divide there. It's X liters underneath the moles on the right side of the equation. And then a half a mole of sodium chloride would be half of 58, which would be 29 grams. So I'm going to put this on quick, only 4 seconds a slide, and you can see how it goes very quickly. I'm just using proportional relationships here. So half of 58, so it's 0.5 moles, so 0.5 cross multiply, and you get 29 grams. Now 500 milliliters, so that's going to be 0.5 liters. So I'm just going to go right to 0.5 liters. So that'll be 2 times 0.5 divided by 1. So it'll be 1 mole, okay? And then what's going to be the mass in grams? So then I'll fill in 101, cross multiply, 2 times, half of 0.5 is 1, 1 times 101 is 101. So then this is going to be 0.25 liters. Same thing, 0.25 liters of 1 mole of a 0.1 molar calcium chloride. And now I'm just going to cross multiply and divide, and it's going to be 0.1 times 0.25 divided by 1, and then cross multiply again, and you get 2.75 grams of calcium chloride. Calculate the grams of solute required to make the following solutions: 2,500 grams of saline solution, 0.9% sodium chloride by mass. Calculate the grams of solute. Well, it would be the percent solution by mass over the mass of solute over mass of solution times 100. You're given 0.9%, so it's going to be 0.009, and then times 2,500, and that'll be the mass of the solute, and that's how much you would need, 2,500 grams of solution. So you'd put 22.5 grams of the sodium chloride into that much solution. Now, 0.05 kilograms of 4% by mass magnesium chloride. So it's going to be 0.004 times 0.05 kilograms, and that would be the mass of times the mass of solution. So whatever that would be, it would be a very small amount of magnesium chloride. So it would be 50 grams or 0.05 kilograms, and then times the 0.04, and it would be 2 grams of magnesium chloride. And then what is the concentration per volume of the following solutions? 25 milliliters of ethanol is diluted to a volume of 150 milliliters with water. So make sure that you understand that it's 25 milliliters of ethanol divided by the volume of solution. The volume of solution. That's the denominator, not the volume of solvent. So it would be 25 over 150, because it says it's diluted to a volume of 150 milliliters with water. So that presupposes that the total solution is 150 milliliters. 175 milliliters of isopropyl alcohol is diluted with water to a total volume of solution of 275 milliliters. So it'd be 175 over 275 times 100, and that will be certainly greater than 50%. So it will be 64%. 175 over 275 times 100 is 64%. Now, what are colligative properties? Identify 3 colligative properties and explain why each occurs. Colligative properties are properties of solution that depend only on the number of solute particles: boiling point elevation, freezing point depression, and vapor pressure lowering. Boiling points are elevated because solvent particles surround solute particles, reducing the number of solvent molecules that have sufficient energy to escape the solution. Relative to the pure solvent, the amount of energy required to cause vaporization or boiling increases. Solutes disrupt the ordering of the solvent structure, so more kinetic energy must be withdrawn from the solution for it to solidify. This lowers the freezing point of the solution. Which has the higher boiling point? You're going to compare various liquids here. Seawater or distilled water? Well, seawater, because it has dissolved solutes, so seawater will have the higher boiling point. B, again, we're going to compare 1 molar potassium nitrate and 1.5 molar potassium nitrate. So the greater one, so it'd be 1.5 molar potassium nitrate. Next, 0.1 molar KCl or 0.1 molar MgCl₂. So it would be the 0.1 molar MgCl₂, because the MgCl₂ will give up 3 particles and the KCl will only give up 2 particles. And that is indeed the case, and that's a very important concept to make sure you understand. 58. Why does a 1 molal solution of calcium nitrate have a lower freezing point than a 1 molar solution of sodium nitrate, because calcium nitrate puts 3 particles in and sodium nitrate puts 2 particles in. So the effective concentration is 3 molar and 2 molar relative to calcium nitrate and sodium nitrate. Explain how a decrease in the vapor pressure of a solution results in an increase in its boiling point. Explain how a decrease in the vapor pressure of a solution. Well, very simple. When vapor pressure is lowered relative to pure solvent, more energy must be supplied to reach the boiling point. Thus, the boiling point is increased relative to pure solvent. Very important concept to make sure you understand. In old-fashioned ice cream makers, a mixture of rock salt, sodium chloride, and ice is used to cool a creamy mixture as it is stirred. What is the purpose of the salt? The salt lowers the freezing point of the ice-water cooling mixture, and it allows you to make ice cream because it's making it freeze at a lower temperature because of all the stuff that's mixed together. Distinguish between a 1 molar solution and a 1 molal solution. A 1 molar solution and a 1 molal solution. 1 molar solution, a 1 molar solution is 1 mole of solute in 1 liter of solution, and a 1 molal solution is 1 mole of solute in 1,000 grams or 1 kilogram of solvent. Okay, so 1 is 1 mole of solute in 1 liter of solution, and 1 molal is 1 mole of solute in 1,000 grams of solvent. Describe how you could make an aqueous solution of methanol in which the mole fraction of methanol is 0.4. The mole fraction of methanol is 0.4. So it would be 27 grams of water to 32 grams of methanol or methyl alcohol. And then number 63 is, what is the boiling point of each solution? A, 0.5 moles glucose in 1,000 grams of water, or 1 kilogram of water. So the change in the boiling point elevation equals Kb, which is the boiling point elevation constant, times the molality, would be, and the molality is moles over kilograms, so it would be 0.5 over 1 times 0.512, which is Kb, and that's going to equal, so 0.512 times 0.5 is 0.256. 0.256 plus 100 is the new boiling point, which is 100.256. What is the boiling point of each solution? 1.5 molar NaCl in 1,000 grams of water. So now we did A, let's do B. Well, there's the equation. Don't forget that the ions now, the number of ions is going to be 2, so you're not going to need as much mass, or that mass is going to have a bigger influence one way or the other. So it's going to be 2 times 0.512 times 1.5, all in 1 kilogram, and that will be the boiling point elevation, the change in boiling point, which is going to be 1.536, so it'll be 101.536, and that will be the new boiling point for the solution of 1.5 moles of sodium chloride in 1 kilogram of solvent. So it's going to be 100, again 100 plus 1.536. and it's going to be 101.536 degrees Celsius. Next, 64. What is the freezing point of each solution? Now we did the boiling point of each solution, now let's do the freezing point. We have 1.4 moles of sodium sulfate in 1750 grams of water. So the number of ions is going to be 3. 3 times 1.86, and the molality will be 1.4 divided by 1.750. And there's the plug-in. And then you want to multiply it out. 3 times 1.86 times 1.4 divided by 1.750 equals 4.464 degrees Celsius, and then it will be negative 4.464 degrees Celsius, which would be the new freezing point of the solution with 1750 grams of solvent. So the new freezing point is negative 4.464 degrees Celsius. Now let's do 0.06 molar magnesium sulfate in 100 grams of water. We have 2 ions, so the number of ions will be 2, 1.86, and then 0.06 divided by 0.1 kilograms, and that will be the freezing point depression. So it'll be 2 times 1.86 times the quantity, 0.06 divided by 0.1. And the freezing point depression, when you multiply and divide that out, will be 2.232. So it would be negative 2.232 degrees Celsius will be the new freezing point, because it's going to be the freezing point of water is 0 degrees Celsius minus the freezing point depression, 2.232 degrees Celsius, and there's the answer. Determine the freezing points of each 0.2 molal aqueous solutions. 0.2 molal aqueous solutions. So there is the equation. Don't forget the number of ions that the salt dissociates into. Potassium sulfate will go into 3. So it'll be 3 times 1.86 times 0.2 is 1.12. So that'll be negative 1.12. The next salt is going to be cesium nitrate. So that'll be 2 times 1.86 times 0.2. And then, so that'll be 0.74. And the next one, C, will be, that's negative 0.744 degrees Celsius. Now it's letter C will be aluminum nitrate. So that'll be 4. So that'll be 4 times 1.86. So times 0.2. So that'll be 1.488. So that'll be the biggest, the greatest freezing point depression will be negative 1.488 for aluminum nitrate. Different numbers of moles of 2 different solutes, A and B, were added to identical quantities of water. The graph shows the freezing point of each of the solutions formed. So you have the green and the blue. Blue is A and B is green. Now, you can see quite easily that the one that causes the greater depression is solute B. So solute B probably is made of more ions than solute A. For instance, solute A might not even dissociate. It might be glucose, and solute B might be calcium chloride, and that may dissociate into 3 ions. Either way, solute B is going to be causing the greater of the depressions for that particular solvent or that particular water, whatever the case may be. Now, it says, explain the relative slopes of the 2 lines between 0 and 2 moles of solute added. So you can see that the more you add of each solute, the greater the distance between the two. So you can see quite easily that what we think is true is probably the case, and that is that solute B is made of or breaks down to a greater number of ions. So the freezing point depression is twice as great as for solute B. Solute B must provide twice as many particles in solution. So it's at least twice as much. Why does the freezing point for solution A not continue to drop as amounts of solute A are added beyond 2.4 moles? Okay, let's go back to the graph, and we can see that at 2.4 moles, solute A remains constant. It remains constant. So, a variety of things could be happening here. Let's read the question again. Why does the freezing point for solution A not continue to drop as amounts of solute A are added beyond 2.4? Well, the answer is this. Solute A probably forms a saturated solution. It forms a saturated solution, so no more A can dissolve. Calculate the freezing and boiling point changes. In other words, the depression and elevation for a solution containing 12 grams of naphthalene C₁H₃ in 50 grams of benzene. And what you'll do is you need the molality, and there's the equation containing the coefficient, the constant for freezing point depression and for boiling point elevation. And M is expanded to include the atomic weight and the mass of the substance. Now we're going to plug in first for the freezing point depression, and that'll be 9.6. So you'll reduce the freezing point by 9.6 and elevate the boiling point by 4.74. And all we did was we looked up the Kf and Kb in a separate table, plugged in for the masses and atomic weights and solvent, and calculated. Very simple. Describe how you would prepare an aqueous solution of acetone in which the mole fraction of acetone is 0.25. That's acetone, CH3COCH3. So, how would you prepare the acetone? Each gram of acetone requires 0.93 grams of water. Each gram of acetone requires 0.93 grams of water. And there's what acetone looks like. Acetone is what you call a ketone. And you see that there's room there for polarity because of the carbon-oxygen double bond. The solubility of sodium hydrogen carbonate in water at 20 degrees Celsius is 9.6 grams per 100 grams of H₂O. What is the mole fraction of sodium bicarbonate in a saturated solution? Well, there's the equation for mole fraction, and we're assuming therefore that Xa is going to be the sodium bicarbonate, sodium hydrogen carbonate, same thing, and now we're going to plug in the values that are given to us. 9.6 because that's the mass, and 100 grams for water, and then we simply plug in and calculate. So it'll be 9.6 over 84. Do the bottom. It's going to be 0.02 is going to be the mole fraction of sodium bicarbonate. So therefore, the water fraction will be 1 minus 0.02, which will be 0.98. So you have a solution by a mole fraction for sodium bicarbonate in water of sodium bicarbonate 0.02 and water 0.98. The solubility of sodium hydrogen carbonate, sodium bicarbonate, in water at 20 degrees Celsius is 9.6 grams per 100 grams of water. What is the molality of the solution? So it would be 9.6 divided by the atomic weight of sodium bicarbonate divided by 100 over 1,000, which would be 0.1. So plugging into the equation, we have 9.6 over 84, which is the atomic weight of sodium hydrogen carbonate, divided by 100 over 1,000, which is 0.1. And we put that into a calculator. 9.6 divided by 84 is the numerator, 0.1 is the denominator, and we get as the molality 1.14 molal. 1.14 molal. So just notice that you're assuming 100 for every 100 grams of water. A solution is labeled 0.15 molal sodium chloride. What are the mole fractions of the solute and solvent in this solution? Well, it's going to be 1.15 moles of sodium chloride per kilogram of solvent. Change the kilograms to moles of water, and you're going to have what is needed. So it will be, there's the equation, and you have the mass over atomic weight. You know that the mole fraction of water equals 1 minus the mole fraction of sodium carbonate, and therefore, plugging into the equation, we can reduce the numerator by just saying it's the moles of H₂O, which is 0.15 moles of sodium chloride, and then in the denominator we put moles of sodium chloride, and then we have to figure out the moles of water, which is 1,000 divided by 18, which will be significant relative to the sodium. And then now we simply plug in. We plug in the moles of sodium chloride, and then we calculate out that the mole fraction of sodium chloride is 0.00269. 1 minus 0.00269 would be the mole fraction of water, and that's going to be 1 minus 0.00269. And if you put that in your calculators, you'll get a very large number relative to the mole fraction of sodium chloride of 0.99731. Mole fraction of water is 0.99731. You are given a clear aqueous solution containing potassium nitrate. How would you determine experimentally if the solution is unsaturated, saturated, or supersaturated? Add 1 crystal of potassium nitrate. If the solution is supersaturated, crystals occur. If it is saturated, the crystal does not dissolve. If unsaturated, the crystals dissolve. Plot a graph of solubility versus temperature for the 3 gases listed in table 16.1. So what I did on the next slide is I put the table of the 3 gases and the solubility. So we have the solubility at 0, 20, 50, and 100 degrees Celsius for each of the gases, hydrogen, oxygen, and carbon dioxide, along with the solubility at each of those gases. So just to note that the gases are listed as grams of solvent per 100 grams of solvent. And there's the second one, that's oxygen, and then I have carbon dioxide coming up. And normally gases are listed, that's carbon dioxide, that's a pretty classic curve which demonstrates the decrease in solubility of the solute as the temperature of the solvent. A mixture of ethylene glycol and water is used as antifreeze in automobile engines. The freezing point and density of the mixture vary with the percent by mass of ethylene glycol in the mixture. On the following graph, point A represents 20% ethylene glycol by mass, point B represents 40%, and point C 60%. A, what is the density of the antifreeze mixture that freezes at negative 25 degrees Celsius? B, what is the freezing point of a mixture that has a density of 1.06? And C, estimate the freezing point of a mixture that is 30% by mass, ethylene glycol. Now what we're going to do is we're going to see each of the graphs, and we're going to examine A, B, and C individually, and we'll take our time. So the graph, freezing point versus density, you can see very clearly that the x-axis is increasing by 0.02 for each major vertical line, and the y-axis is degrees Celsius. What is the density of the antifreeze mixture that freezes at negative 25 degrees Celsius? So you can see clearly that it's going to be approximately 1.14. What is the freezing point of a mixture that has a density of 1.06? And that's going to be approximately 7.2. How they can read the 0.2 is beyond me, but around 7. Estimate the freezing point of a mixture that is 30% by mass. So 30% by mass. So you have the dots, 20 and 40, so halfway would be approximately 30, and that would be negative 9.5. Calculate the freezing point and boiling point of a solution that contains 15 grams of urea, that's CH₄N2O, in 250 grams of water. Urea is a covalently bonded compound. That's a dead giveaway for a non-dissociating compound. There's the equation for the freezing point depression. Now we're going to put in the various factors. You can see I don't even have N for the number of ions in solution because it's not going to ionize. So I'm going to also put in the boiling point elevation is there. I plugged in for the freezing point depression, that's 1.06, and then because 15 over 60 is 1/4 and 250 over 1,000 is 1/4, so the freezing point would be negative 1.86 degrees Celsius, and then the boiling point, the only real difference is going to be the 0.512 degrees Celsius per molal. So the temperature, so the boiling point elevation would be 0.512 degrees Celsius, and the boiling point would be plus 0.512 degrees Celsius. Calculate the mole fractions in a solution that is 25 grams of ethanol and 40 grams of water. Well, remember that the mole fraction of one substance is going to be complement to the other. In other words, 1 minus the mole fraction of ethanol will be the mole fraction of water, and vice versa. There's the equation for the mole fraction expanded for mass over atomic weight for moles, plugged in to the equation. So the mole fraction of ethanol is going to be 25 divided by 46 divided by 25 divided by 46 plus 40 over 18, and that's going to be a very small fraction of this is going to be ethanol. Capital E, capital T, capital O, and H is the abbreviation for ethanol, so that's going to be 0.2 ethanol, and so therefore it would be 0.8 water. So the mole fraction of ethanol is 0.2, and you'll see in a moment that the mole fraction of water will be 1 minus 0.2, or simply 0.8. 0.8. Just remember that when you calculate the mole fractions, if they don't add up to 1, then there's a major problem somewhere. and so they have to add up to 1, and the numerator divided by the sum of the moles in the denominator. This is the molecule urea, and you can definitely see areas that are polar. Estimate the freezing point of an aqueous solution of 20 grams of glucose dissolved in 500 grams of water. This is all the data you need, and at this point it should be fairly simple. That's 180 is the atomic weight of glucose, and it'll be negative 0.413. The solubility of potassium chloride in water is 34 grams of potassium chloride, 100 grams of water at 20 degrees Celsius. A warm solution containing 50 grams of potassium chloride in 130 grams of H₂O is cooled to 20 degrees Celsius. How many grams of potassium chloride remains dissolved? So let's set a proportional relationship. 34 over 100 is A over 130. So that means that A equals 44.2 grams. So I can fit 44.2 grams there. How many grams came out of solution? Well, it's going to be 50 minus 44.2 grams is 5.8 grams. How many moles of ions are present when 0.1 mole of each compound is dissolved in water? Potassium sulfate, that'll be 3. Sorry, 0.3. 3 times 0.1 is 0.3. B, iron 3 nitrate, that'll be 0.4 moles. C, aluminum sulfate, that'll be 5.5 moles because it'll be 5 ions. Next, nickel 2 sulfate, that'll be 2.2 moles. A solution contains 25.6 grams of sodium chloride, 75 grams of water at 20 degrees Celsius. Determine if the solution is unsaturated, saturated, or supersaturated. The solubility of sodium chloride at 20 degrees Celsius is 36 grams per 100. So let's set up a proportional relationship. 26.5 divided by 75 is going to be what over 100? If it's greater than 36, then it's going to be saturated. If it is 36, it'll be saturated. And it is 35.3, so it is unsaturated. Work it out. 26.5 times 100 divided by 75 is 35.3, which leaves it unsaturated, or less than that for less than 36 grams per 100. An aqueous solution freezes at negative 2.47 degrees Celsius. What is its boiling point? Okay, so there's the freezing point depression equation. We know what the freezing point depression is. That's 2.47. Solve for M. M is 1.33 molal. Put in the equation for boiling point elevation. We plug in the molal. We know what the constant is, 0.512. The boiling point elevation is there, and then it's going to be the new boiling point elevation that will make it plus the 100. Hydrogen peroxide is often sold commercially as 3% by mass volume. If you buy 250 milliliter bottle of 3% hydrogen peroxide, mass and volume, how many grams of hydrogen peroxide have you purchased? 3 over 100 equals X over 750, and that's going to be 7.5 grams. Hydrogen peroxide is often sold commercially, what is B is what is the molarity of this solution. So remember, molarity is moles over volume of solution, not volume of solvent, but volume of solution, and that'll be 0.88 molar. How many grams of sodium nitrate will precipitate if a saturated solution of sodium nitrate in 200 grams of water at 50 degrees Celsius is cooled to 20 degrees Celsius? There's 88 over 100 at 20 C, and then X over 200 grams of water at 20 C. X is 1 176 grams of sodium nitrate. There are 176 grams of sodium nitrate dissolved in 200 grams of water at 20 degrees Celsius. The solubility of sodium nitrate at 50 degrees Celsius is 114 per 100 grams. There will be a total of 228 grams of sodium nitrate dissolved in 200 grams of water at 50 degrees Celsius. Therefore, 228 minus 176 is 52 grams precipitated out solution as the solution cools. What is the molar mass of non-dissociating compound if 5.76 grams of the compound and 750 grams of benzene gives a freezing point depression of 0.460? There are the equations that you need, including the expanded version of the freezing point depression and the number of ions, which is N. That's the portion of the equation that you need. Plug in, it's going to be 1 because it's non-dissociating. It's going to be N, 5.12, and there's the other values. And so you solve for the atomic weight. So we're going to we're going to plug in for 0.460, and then we're going to solve for the AW. Okay, so you're going to rearrange things, and you're going to solve for AW. So you're going to say 0.46 times AW times 0.75, and then 0.75 times 0.46. I'm just showing you the math here. Make sure you can do this by yourself. Try to make this calculation yourself. So the atomic weight is 85.5. Now that could be molecular weight, formula weight, whatever. I just say atomic weight for a general term. The molality of an aqueous solution of sugar is 1.62. Calculate the mole fraction of sugar and water. So it's going to be 1.62 moles of sugar over 1,000 grams of water. That's what 1.6 molal means. So the number of moles of water is going to be 55.6 moles of water. So it's going to be 1.62 divided by 1.62 plus 55.6 is going to be the mole fraction of the glucose. So let's watch and see. I'm taking my time with this particular problem. See if you can do the problem before it finishes here. Why don't you put this on pause and let things run out a little bit. I'm just going to be quiet and let the problem play out. And so the water will be 1 minus 0.028, and the answer will be for glucose 0.028 and for water 0.972. Why might calcium chloride spread on icy roads be more effective at melting ice than an equal amount of sodium chloride? Because you get 50% more ions in solution with calcium chloride. Calcium chloride produces 3 particles. Upon dissolving, sodium chloride produces only 2 particles. Freezing point depression depends on the number of solute particles in the solvent. Remember, colligative properties is based on particles, not the identity of those particles necessarily. The following table lists the molar concentrations of the most abundant monoatomic ions in seawater. Calculate the mass in grams of each ion contained in 5 liters of seawater. The density of seawater is 1.024 grams per milliliter. So there you have the first one, 35.4 grams. Notice the more precise measure of chlorine, and that's going to be 1 mole of chlorine, and then 0.546 moles, and that's going to be ultimately multiplied by what? So these are the various values for the concentration. But I've got to correct this for 5 liters. I've got to correct this for 5 liters. So I'll let this run, and there's the first one times 5 liters, and it's going to be 96.5. Notice I took the value for the moles, the mole equivalent, and the atomic weight, and that's going to be, for instance, that'll be the 19, and then multiplied it by 5 liters, and that's the value, 96.5, and the liters will cancel. Okay, which will have a greater boiling point elevation, 3 grams of calcium nitrate in 60 grams of water, 6 grams of calcium nitrate in 30 grams of water. The solution with the higher concentration of ions will have the greater boiling point elevation, 6 grams of calcium nitrate in 30 grams of water. Now, the next one is going to be very involved, and it's almost like a final exam in and by itself. Let's read it. When an excess of zinc is added to 800 milliliters of hydrochloric acid solution, the solution evolves 1.21 liters of hydrogen gas measured over water at 21 degrees Celsius and 747.5 millimeters of mercury. What was the molarity of the acid? The vapor pressure of the water at 21 degrees Celsius is 18.6 millimeters of mercury. So it's collected over water, so we know that that's going to be quote-unquote wet hydrogen gas. So what's the partial pressure of water in that wet gas at 21 degrees Celsius? And it's going to be 18.6 millimeters of mercury. Therefore, I have to correct for the pressure of the hydrogen, which is wet hydrogen gas, subtract off 18.6, and you're left with dry hydrogen gas. Now you can see that there is some interesting material here relative to gas laws, moles, etc. And what I'm going to do is I'm going to employ gas laws to help me answer the question. Now, you need a stoichiometric equation, and that's going to be coming up soon. And what I'm going to do is I'm going to shorten the amount of time per each slide down to 3 or 4 seconds, and you'll be able to see how this problem progresses. You should be able to do this problem on your own, and that's very important to understand. If you can do this problem on your own, do it once with me and then go back, you're going to be very well prepared for the final exam. And now I will just let this go, and I'll come back in a minute or so. This is the stoichiometric equation with the appropriate masses, etc. This is the first set of conditions, correcting for T1, making it Kelvin, We'll do the same thing with T2, and we're going to be having to solve for the new volume. That's a critical part of this. Why are we solving for a new volume? That's a question. Have you figured any of this out yet? There's the combined gas law equation. Those are the values. And you're going to solve for V2, which is 1.08 liters. Now what? What are we up to now? Well, I know the mass of H2 because 2 grams is 22.4. In 1.08, there's going to be 0.964 grams. So now I know how many grams. 0.0964. So now I need to know how many grams I actually used. There's my constant ratio, hydrogen to hydrochloric acid. Notice I'm using 72.8, which is, I'm using a little closer value using the atomic weights, more specifically 35.4 for chlorine. So now that gives me the mass of hydrochloric acid. I have the mass of hydrochloric acid, that's 3.51 grams, and 36.4, which would be HCl, and that's the value. Let's summarize that a little bit before we quit. So what I did was, using the method of mass to mass, etc., and using the relationship between volume and moles at STP, I determined that I had 3.51 grams of HCl, and I had 800 milliliters of solvent. So I know the number of moles of HCl was 3.51 grams of solute per 36.4 grams for 1 mole, and then I know that I had 800 milliliters, so how many moles did I have in that? Well, the number of moles I had in the 800 milliliters of HCl was 3.51 to 36.4, and then I divide all of that by 0.8, and that equals 0.12 molar. A fairly dilute solution of HCl, fairly dilute. How many milliliters of 1.5 molar nitric acid contains enough nitric acid to dissolve an old copper penny with a mass of 3.94 grams? So there's the stoichiometric equation, and we're assuming that the penny was pure copper anyway. So 190.5 grams and 504 grams of the nitric acid are the stoichiometric masses. 3.94 is to X. So there's my constant ratio, 190.5 divided by 504 equals 3.94 over X. Solve for X, and the answer is 10.4 grams of nitric acid. So now I have 10.4 grams of nitric acid, and I'm looking at how many milliliters of the 1.5 molar solution is that contained in. So I have 0.165 moles of nitric acid that I'm using, and how many milliliters will that be? And the answer is 110 milliliters of the 1.5 molar solution of HNO3. One way to express the solubility of a compound is in terms of moles of compound that will dissolve in 1 kilogram of water. Solubility depends on temperature. Plot a graph of the solubility of potassium nitrate from the following data. From your graph, estimate A, the solubility of potassium nitrate at 76 degrees Celsius and 33 degrees Celsius. The temperature at which its solubility is 17.6 moles per kilogram of water, and C, the temperature at which the solubility is 4.24 moles per kilogram of water. So I'm going to graph the data, and I'll show you the graphs, and then I'll draw lines connecting the axes with the curves. And then you simply have to, for a given x, plot the corresponding y, and for a given y, plot the corresponding x in terms of temperature and solubility. So there's the graph. Let's reread the question really quickly. One way to express the solubility of a compound is in terms of moles of a compound that will dissolve in 1 kilogram of water. That's molality. Solubility depends on temperature. Plot a graph of the solubility of potassium nitrate, KNO₂, from the following data. There's the data. Let's make the plots. And all I did was I just did it on Excel myself. There's the plots, pretty good plot, pretty good smooth curve. And there are my points that I'm going to find relative to the question. 76 degrees is going to be the corresponding values for 76 degrees Celsius and 33 degrees Celsius are 15.2 moles per kilogram and 5 moles per kilogram respectively. B, the temperature at which the solubility is 17.6. Temperature at which the solubility is 17.6 moles per kilogram of water. Let's go to the graph. And we see that it is specifically approximately 82 degrees Celsius. 82 degrees Celsius. The temperature at which solubility is 4.2 moles per kilogram. And it's going to be approximately 22, 24, a little over 24, 28, 28.5. Next, a 250 milliliter sample of sodium sulfate is reacted with an excess of barium chloride. If 5.28 grams of barium sulfate is precipitated, what is the molarity of the sodium sulfate solution? There's the equation, the balanced equation. There's the stoichiometric masses. Let's see what unfolds. Hold on. Solve for X. There's my ratio, my constant ratio, 3 coppers to 8 nitric acids, 190.5 over 504, and then solve for X. Suppose you have an unknown compound and want to identify it by means of molar mass. Design an experiment that uses the concept of freezing point depression to obtain the molar mass. What laboratory measurements would you need to make? What calculations would be needed? Think. Put it on pause. Don't read the answer. Determine the freezing point of a suitable solvent. Dissolve a known mass of an unknown molecular compound in a known mass of the solvent. Determine the freezing point of the solution. This gives the freezing point depression. Use the freezing point depression equation as shown. M to find the molality of the solution. What's next? Think. Use the molality to find the moles of solute. Use the moles of solute and the measured mass of solvent to calculate the molar mass. The molar mass obtained is valid only for an undissociating molecular solute. A cylindrical vessel, 28 centimeters in height and 3 centimeters in diameter, is filled with water at 50 degrees Celsius. The density of water is 0.988 grams per cubic centimeter at this temperature. There's the volume. There's the pi r squared h. So the volume is going to equal what? What is pi times 1.5 squared times 28? And the answer is 198 cubic centimeters. That's the volume. We know the density. Now we have to find the mass. The density equals rho equals mass over volume, and mass equals rho v, and then mass is going to equal 0.988 times 1.98 equals 196 grams. And then we want to do some conversions with 196 grams. Express the mass of water in the vessel in the following units. Grams, so it's 196 grams. I think it's going to be milligrams is next, so you're going to multiply it by 1,000. So that'd be 196,000 grams, milligrams. And then kilograms would be 0.196 kilograms. And in kilograms, 0.196 kilograms. And that's correct. Next. Convert each of the following mass measurements to its equivalent in kilograms. So the first one is going to be 0.347 kilograms. Moving the decimal place over, that's what we're doing, working with base 10. 3.47 times 10 to the negative 1 kilograms. 73 milligrams. And it's going to be 0.000073 kilograms. And that'll be 7.3 times 10 to the negative 5th kilograms. And just let it keep going. I'll let it play out. You watch, see if you can do the problem before I put it up. I think I'll change the timings on these. It seems like it's a little bit long. You should be able to do these much more quickly. Okay, let's continue. Had a hard time changing the timings. I don't know what's wrong with it, but it's playing well. So just let's keep it going. What is the most significant difference between the Thomson model of the atom and the Rutherford model of the atom? Rutherford's model contains a nucleus. Very interesting. Oh, that's a flash from the past, huh? Name and give the symbol for the element in the following positions in the periodic table. Group 7b, period 4. Group 7b, period 4. Manganese. Manganese. I see. And let's just let this run out. This is pretty much just looking at a periodic table. Let's see. Let's keep it going. I'll let it run till the next question. How many atoms of each element are present in 4 formula units of calcium permanganate? Calcium permanganate, 4 formula units contain 4 calcium atoms, 8 manganese atoms, and 32 oxygen atoms. Because calcium permanganate is Ca quantity MnO4 2. Terephthalic acid is an organic compound used in the synthesis of polyesters. Terephthalic acid contains 57.8% carbon, 3.64% hydrogen, and 38.5% oxygen. The molar mass is approximately 166 grams per mole. What is the molecular formula of terephthalic acid based on 100 grams? I am going to let this go because you have to determine the empirical formula and then divide the empirical formula weights into the molecular mass, the molar mass, and then that will give you N, and then multiply the empirical formula by N, and you'll get the molecular formula. So I'll let this run out. I'm right now determining the moles of each element involved. So there are my values. My empirical formula is C₄H₃O₂, and the mass of that's going to be 83, and then it'll be 166 divided by 83 is 2, multiply everything by 2, N is 2, so it'll be C₄H6O4. The photograph shows 1 mole each of iron, copper, mercury, and sulfur. All right, it's easy. Excuse me. So what is the mass of each element? Mass in grams. There they are. Remember, the mass in grams of 1 mole of any particle is equivalent to the mass of 1 particle in atomic mass units. How many atoms are in each sample? 6.02 times 10 to the 23rd, because that's the number of particles in 1 mole. What else? All right, going back to the original question. How many moles is 25 grams of each element? How many moles is 25 grams of each element? So it'll be the mass in grams divided by the atomic mass. And so 25, 25, 25, 25 divide by the atomic weight of each, and it will be, the atomic weight for each will be, I think iron is 56, 64, 201, and 32. So divide, make those quotients. So 25 divided by 56, 25 divided by 64, divided by 201, divided by 32, and you get 0.45, 0.39, 0.12, and 0.78 moles, respectively. What is the volume occupied by 15 grams of hydrogen gas at STP? Well, each is going to be, each 2 grams is going to be what volume? So it's going to be 1,500 grams divided by 2, that's going to be the moles, then R, then temperature, then the pressure, and then you calculate the volume. Identify the type of chemical reactions. The first one is synthesis, decomposition, single displacement, combustion, single displacement, and lastly, double displacement. And there we go. So S, decomposition, single replacement, combustion, single replacement, double displacement, double replacement. Write the net ionic equation for the following reaction. I think I did. I'm not sure what that means, but indicates by simple equations how the following substances ionize or dissociate in water. So that's going to be NH4 plus 1 plus Cl minus 1. Let's see if that's right. That's right. And notice they're going to be aqueous. Ammonium chloride is a solid at room temperature, undissociated. Copper 2 nitrate would be Cu plus 2. See that 2 on the right of the nitrate. And then plus NO3. NO3 with a minus 1 charge. And then nitric acid would be plus 1, and H plus 1 and NO3 minus 1. And I'll just let this run out. I think we're going to do DEF. By the way, that's acetic acid. We'll study that a little bit in chapter 19. The equation for the composition of methanol is the following. The equation for the combustion of methanol. So 2 methanol plus 3 oxygen yields 2 carbon dioxide and 4 water. The stoichiometric masses are 64 grams for methanol and 96 for oxygen. What volume of oxygen measured at STP is required to completely burn 35 grams of methanol? I am not going to answer that question. I'm going to let you answer the question, and I'm just going to roll the problem here and see if you can come up with the answer. I'm just going to be quiet. So it's going to be 37 liters of oxygen, and that's going to be X. Draw electron dot structures for the following atoms. So there's a whole bunch of atoms here. It's the valence electrons, so I'm just going to let this roll too. Iodine and tellurium. Antimony. A cylinder of nitrogen at 25 degrees Celsius at 101.3 kilopascals is heated to 45 degrees Celsius. What is the new pressure of the gas? So a basic Gay-Lussac problem, P1 over T1 equals P2 over T2, and just plug in and grind it out. Plug and chug. Why does an ideal gas not exist? A point of contention with my classes during chapter 14. Interesting question. The particles in an ideal gas have no volume, and there are no attractions between the particles. I think at certain temperatures, real gases it's a difficult egg to crack. What relationship exists between surface tension and intermolecular attractions in a liquid? Hydrogen bonding increases surface tension. Unbalanced intermolecular attractions between molecules at the surface of a liquid and those below the surface create an inward pull or force that minimizes the surface area to create surface tension. The solubility of hydrogen chloride gas in polar solvent water is much greater than its solubility in the nonpolar solvent benzene. Why? The very polar hydrogen chloride molecule produces hydronium ions and chloride ions that are stabilized by becoming surrounded by water molecule solvation in aqueous solutions. Hydrogen chloride does not dissociate. Let me change the timing on that. Let me read that sentence again. Hydrogen chloride does not dissociate in nonpolar benzene. Polar compounds generally have low solubility in nonpolar solvents. And last problem, 2 hours later, when soap is shaken with water, is a solution a suspension or a colloid formed? It is going to be an emulsion, a colloid. A solution, if the soap mixture is very dilute, true enough, more concentrated mixture of soap in water form a colloid. It would not necessarily be an emulsion because it's not emulsifying anything, but many of you would say that it's emulsion, but it's really not emulsifying something. So if it's the soap molecules can be rather large, depending upon the number of carbons in them. But I like the answer that they just gave. All right, lecture is going to be the next thing to be posted. Hopefully I can do that this weekend. Have a good day. Please look over these problems, and all the best next week.